Hello everybody, welcome to this long-awaited video. For those who don't know me, allow me to introduce myself. My name is Matheus Luquezes Guissardi. I am a mechanical engineer with a MBA in project management, and I am a Lean Six Sigma Master Black Belt. I have over 10 years of experience with the Six Sigma methodology, whether solving problems, guiding projects, coaching and mentoring people in their own projects, or implementing continuous improvement programs in different companies. So during the past 12 or 13 years, I have worked with the methodology in various areas of companies, including quality, engineering, processes, laboratories, technical support, reliability, and more. Since 2020, I have been the co-founder of Plan A, Operational Excellence, a consultants company that I can now start calling multinational because we are in Brazil, but it started operating in different languages across different countries. So in the company, I work as a consultant and instructor of all our training programs, while my partner and wife manages the entire administrative side. Okay. I started this YouTube channel with the goal of helping people use JMP software in their analysis after training. So I recorded more than 40 videos in Portuguese, another 40 videos in Spanish, and 40 videos in English. So I really hope I have helped many of you. Okay. So last year, a colleague and I recorded a few videos comparing the use of Minitab and Jump, okay, for problem investigation using the Six Sigma methodology. So we created three videos, one at the yellow belt level, one at the green belt level, and the last one at the black belt level. So I used Jump while Hobson used Minitab. So in my opinion, they were pretty good videos, but all the videos were recorded in Portuguese. After that, I attended an event in the US where I met many people and we talked about problem investigation, we talked about softwares, we talked about Six Sigma methodology, quality, continuous improvement. And when I talked about these videos that were recorded in Portuguese, they asked, please, Mateus, record them in English because they would be very useful. So here I am, okay? After receiving this request, I registered on Minitab. I learned how to perform the analysis, and now I'm finally here to record this comparative video between the two software tools, okay? This time, we will investigate a problem at the green belt level, one of the most, let's say, recognized certifications in the world when it comes to Six Sigma. Okay, and before we jump into the comparisons, I just want to say big thanks uh, for being here, for supporting this small YouTube channel, and for your like and possible comment or sharing. Okay, so let's do it. Let's get started. So, how it will work? Okay, we will compare Jump software against Minitab software with these different criterias: availability, usability, functionality, and performance. So as you can see, I'm using Mac OS, okay? And when I went to download the Minitab software, uh, I could not download it because the desktop app is Windows only. So I will use the Minitab as a open web app. I I am a little bit limited here, but I have to say to you that Minitab is at a disadvantage here, but whenever a tool is limited in this case, I will point out what could be done differently in the desktop application. But here is something that, for example, Jump software earns a trophy because availability. So we don't have Minitab for Mac OS, and I know a lot of people that use Mac OS. So every time that a software here performs better, it will earn a trophy. So this is how it works. We will evaluate the ease of use, the user experience, understanding of analysis, the range of features, customization, interactivity, the speed, the statistics involved in the analysis. So we have here an Excel file. We have some different tabs here. For example, the problem approach. We will have a Six Sigma Green Belt approach. We have the start of investigation. We have the project charter. We have the process map, where we are looking for the main sources of variation, the main variables here. Our hypotheses are here. So we will evaluate the measurement system. We will go to the process and run a sampling plan, collecting data. The data are already here. We have a DOE plan here with 5 different factors in different levels, in 2 different levels. We have some noise strategies. We have the DOE data here. We will analyze the DOE with JMP and the Minitab, and we will finish this video running the validation analysis comparing again Jump versus Minitab software. Okay, so let's start. Let's start with the problem approach. No, let's start with the project charter. So let's talk about the problem. So to understand the situation here, imagine that you are in a movie theater with your family and suddenly the air conditioning system stops working. So anybody has no idea why it's happening, but it gets very hot and you have to get out of the movie theater. You are very upset and maybe you won't come back there for a new movie, okay? So we start to investigate what happened, and suddenly, some people discover that this little rubber ring fell off the electrical motor. So this electrical motor drives the entire system, the entire air conditioning system. So this is a very, very serious problem that needs to be understood and solved. So when we start solving this problem, investigating this problem at Plan A consultants, for example, we always use a Six Sigma project charter. We have to be very clear. We have to describe the situation. So we have here a part for the candidate information, the project information. So the project, what is the project? The project title is the the attachment of the motor ABC rubber ring, and technically speaking, the objective is what? Is understand the factors affecting the rubber ring's detachment and ensure that the traction force is at least 300 kilogram force with CPK more than 1.33 within 6 months. This is the objective. The current situation, the description. These rubber rings are applied at the interface for securing air conditioning components. The interface consists of an aluminum piece and a rubber piece bonded with adhesive. Okay, there is a glue there. The bonding process is internal, and there is a duplication of suppliers for both the adhesive and the rubber ring. The process is not expensive, but is not robust, as there are customer complaints regarding poor rubber fixation. So we have a situation here. The main hypothesis at the starting of the project investigation are variation in the amount of adhesive applied, fixation method is not robust, different adhesive suppliers, dirt on the surface where the adhesive is applied, and insufficient curing time. So here we have our project charter with the information that we need to get a sponsorship from the managers, mainly the candidates manager and the project application area manager. So this is our project charter. And now let's take a look on the process map. The main objective for the process map is to understand the main source of variation for the rubber ring fixation process. So we separated the process in three main steps. The first one is to prepare components and apply glue. We will start saying glue instead of adhesive. And the second one is to attach the rubber ring to the cover. And the last one is measure extraction force. So everything that we write here, that we list here, will directly affect the sampling plans. For example, how we will run an MSA, which of the sources of variation that we will put here, and the components of variation, and the factors and the levels for a DOE, they all should come from a process map or a product map. So we have some things that are controllable, and we have some things that are not controllable. They are noises. So we should list here, and this is what we are doing here. We are investigating a problem. So what are the hypotheses? Okay, they are all here. The amount of glue, the glue application position can be in the rubber or in the aluminum, the impurities on the aluminum surface, the impurities on the rubber ring surface, part shape errors. Here, the moment that we are attaching the rubber ring to the cover, we describe it here: fixation time, fixation method, can be manual, can be assisted. The glue supplier, we have different suppliers, so they could cause this problem. Rubber ring supplier as well. And the moment that we are measuring the extraction force to understand the problem, to investigate the root cause, we have the extraction equipment, we have the operator that are measuring this, and we have, for example, the ambient temperature. So everything here can affect the problem, so we should study them in some time, okay? So now let's talk about the MSA, the measurement system analysis. So what was done here? We have five different group of parts, because it's very important to mention that this study is not repeatable. It's a destructive study, because every time that we measure a part, the part is destroyed. So it is impossible to extract the part and measure, attach again, and measure it again. So we separated here five different groups of parts. We have two different measurement equipment, the gauges, and two operators. So we have a total of 20 data points. I will select the data table here, and I will start analysis with the Open Lab app for Minitab here. So we have two different ways to analyze a measurement system, the easy way and the hard way, let's say. I will start with the hard way. Okay, so I will paste the data here. When you open the stat part here in Minitab, inside of quality tools, you will find this gauge study. So once you click here in this gauge study part, you will have a lot of different options. This is very nice, but you have to know everything that you are doing because there are some differences between crossed, nested, and expanded. So let's focus on these gauge RNR studies. The crossed one is that one that you can repeat the measurement. You can repeat, you can measure it again. You can measure like 20 times the same part for using different gauges or people. All right. So this is not the case. The expanded one is that one that you not necessarily repeat the measure, you can change the equipment, you can add some different factors in your study. And the nested one is the one that we are using here because we are not repeating the measurement. Okay, so let's pick this one, nested. So the part or batch numbers, look that we have these batch numbers here. So it's our group of parts. The operator is here and the Y, our response variable, is here. There are some options inside here. The gauge info, the options we could put here, for example, our lower specification limit. It's about 300 kilos. So let's put here and OK, let's click on OK, and we will have here our analysis. Okay, so we have lots of information. Gauge and are nested. We can see the various components here, and here we have a problem because the Minitab software is considering the repeatability here, and we are not repeating. Why is happening here? We we had the options of putting there the parts, the operator, and the response variable. We didn't have the option of adding the equipment in this study. So maybe we should use the expanded one, okay? So let's run the nested one to do a fair comparison between Minitab and JMP. So here for me, we are doing it wrongly, okay? And if we are doing here wrongly, repeatability, we are considering a number, of course, here we will be wrong as well. But the risk is low, and for this specific case, I won't be worried because the part-to-part variation, we are talking about 99% of the study. So we have some probabilities and we have some graphs here that could help you in a easy way. Let's say the X bar, the R chart, and some graphs that can show us that part-to-part variation is so much bigger than the repeat and reproducibility. Okay, so if we have to copy and paste here, we just copy the graph and we go to our Excel file and we just paste it here. But here, using this web app, we have a problem because when I have to copy this information, copy table, I will have this table, literally the table. So it's not what I have, what I need here because I don't need the table, the information like that. I would like to have a picture here. Okay, so if you want to copy the picture from here, you will have to use your screenshot, your app to copy and paste your pictures. Okay, so let's run this. This is not so easy. It should be easier, okay, but we have this information. So this is the hard way of analyzing an MSA, in my opinion, okay, because we could be more specific or more practical, okay? So how could we be more practical analyzing an MSA using Minitab or JMP? Let's run something called variability chart. We have here variability chart inside of these quality tools. It's so much easier analyzing using this graph. Response, why? The factors, look, the factors, group of parts, equipment, and operator. Lab is not fair putting lab here because it's the same lab, and the measure is not fair as well because each part, each combination has only one measure. Okay, so let's run this graph. It's a easy graph to analyze, so we can just copy this graph and paste in our report, being Excel, Word, or PowerPoint, whatever. So here, let's zoom in here. And here we can see what? The group of parts number one. We have the equipment one being used by the operator one and two. The results are very, very close to each other. So they are very similar. We change the group of parts and we have a change in our values. So we are seeing practically that the results are good. The results are not good when we compare to the lower specification limit. All the parts here are not approved because we should have at least 300 kilos in our extraction force. So we are seeing that with only 5 different groups of parts that we don't have the specification being achieved here, okay? So this is a very practical analysis. We are talking about our measurement system analysis or evaluation. So we can consider that we could consider without any stats, without any number here, that we are having so much more variation between parts than between operator or equipment. Okay, so this is it. So that's how we could analyze the data using Minitab. If I wanted to change here the operator and equipment, I should run again this graph. Okay, so variability chart, and I want to change the sequence. So I want to put operator and equipment and I will have a different graph because equipment is here and operator is in the middle. Okay. To add the specification limit here, if I were using the Minitab app, desktop app, I would just go in here in the options of the axis, and I will just add a reference line here, and that's it. But here in this web application, I don't have this option. Okay, if you know how to add a reference line here, please let me in the comments how I could do it. And the last part here that I like to run doing MSA is the stat. Okay, if you want a stat, let's run it. So you could just go in here, ANOVA, fully nested ANOVA, and you just put your Y here and your factors. Oops, it's not here. Is here equipment operator. So equipment and operator and group of parts. And now you have variance components about your factors. Okay, so let's capture this little information here and let's paste in our report. So by doing this, we can see that 99.95% of our total variation is due to group of parts, 0.01 to the equipment, and 0.05 is due to operator. So this is a very good measurement system. It is approved and we can move on to the COV analysis. But before that, we will run a JMP analysis with the same data. So now we will copy the same data table and we will run this analysis in JMP. So I just pasted here the data, and again, we have the easy way and the difficult, the hard way to run this. If you need more stats about the information that you have, you can just go here in this measurement systems analysis inside of this quality and process platform, or you can use the variability chart. This is the easy way and this is the hard way. Let's start with the hard way to compare with the Minitab. So we have this platform here. Extraction force, it's here. Something that I have to change here, it's those columns because they are nominal, they are source of variation. They are continuous here because they are numbers. So I have to change here. It's an important step. So part is group of part, and equipment and operator, they are the X. Okay. So gauge R&R nested. Okay, let's click here. And we have this graph. This is a variability chart. We could connect here. This is a difference between Minitab on web, or even if you are using Minitab as a desktop application, if you have to change here, you have to run the chart again. So this is something that is an advantage in JMP because this is very interactive. And let's run the analysis. So gauge studies, gauge R&R. So the lower specification limit, let's put here. Okay, it was a message that your parts are not good. We have a lot of information. We have to be sure that you are using the right column for the right information. So group of parts for part, okay. So here, something that is very interesting using JMP is that JMP understood that we are not repeating the measurements. So repeatability, we have zeros, 0, 0, 0 here. So this is very, very important. We are calculating the reproducibility due to the operator and equipment. And there's an information here that is equipment is nested within operator, so this is important. Our gauge NRR is 29%. We have here part to part being like 85%. So now we can just copy here. How can we copy the information from here to our report? So we have these gray buttons here. Just click with the right button, right click on your mouse, edit, copy picture. You go there and you paste your information. So everything is in a picture. So this could be compared with this. Oh, but there is no graphs like Minitab. Okay, you can go here and ask for some plots. So you will have some different plots here. Let's make them smaller to copy them. So if you want to copy these graphs, you just could come here, right click, copy picture, and copy this information. So let's compare the easy way. Let's run a variability chart. So analyze, quality and process, variability. This is the same platform, but here, instead of having the gauge R&R, we will have the variability option. So extraction force, group of parts, equipment, and operator, uh, and that's it. Okay. So here we have our variability chart. We can connect cell means. We can double click here and add our specification limit, like lower specification limit. Let's choose a dashed blue line, and we could have this information. We see that the parts are not good, but our interest here is being sure that the part-to-part variation is bigger than the equipment variation or the operator variation. So this is a very good measurement system. It is approved. We can just copy this picture and paste it here. And we have this last part called variance components. JMP asked me what type of model you want. You can choose main effect, crossed then nested, nested then crossed. So the range of applications here is bigger, and I think is a little bit easier to understand and to pick the right option or to run the analysis. So to be fair, I will compare using nested as you used in Minitab. So nested here, and we have the analysis of variance, and we have this little box here that we could compare with the Minitab results. So the variance components, okay? Let's compare them. 99.9, 0.006, and 0.04. So rounding up the numbers here, we would have, I think, the same numbers. For example, the total variation 187.75, and here the same 0.75. Okay, so that's it. Comparison between Minitab and JMP software running a MSA analysis. You see that there is a hard way and this is a easy way. Okay, so sometimes it's better to be more practical than statistical and being sure that what you need is what was done. Okay, so now we will talk about the CLV, the components of variation. What is the main goal here when we are running a CLV? The idea is to go to the processes and to understand what is happening. What are the main sources of variation? What is causing more effect or not in our results? Okay, so we are looking for a content action that we will understand the process variation, the voice of the process, and we will act to stop something or to pick the best solution for the moment. Okay, but here we are trying to make like an experiment because the investigator here he went to the process and he tried to combine different rubber suppliers with different glue suppliers. So imagine that we had two different suppliers for the rubber, two different suppliers for the glue, and we got like five different parts for each combination. So let's understand which one is causing more variation in our process. So that time, at this time, I will start with the jump software. I will create a new table here. I pasted the values here and I will start analyzing. How we will start analyzing using jump? Analyze quality and process variability. So variability is one of the best graphs to run this type of analysis because we don't need a control chart. We, we don't need a control chart. I will explain why. So here is a simple graph. We have everything that we need here. We have all the 20 data points separated by glue suppliers and rubber supplier. We can see that we can put our specification limit here, our 300 kilos, blue dashed line. Let's see what will happen here. Oops, three. Oh, it's not labeled. It's here. The value is here. It is our lower specification limit. Oh, sorry about that. So here is our specification limit, our lower specification limit, and we can see in a very, very practical way that we don't have good parts. All the parts are below our lower specification limit, so we are not good. But we can see that if we had to pick the best solution for the moment, is not a good solution, but is the best solution. We should pick the rubber supplier number two and the glue supplier number one. So this is a very, very practical analysis that we can copy and paste right here. So we just started our analysis doing this. And what more could we do here? We could run these variance components. And now a lot of my students they understand, they had this training when almost always said that when we are running a COV, all the studies are nested. But this one is not nested because we are changing, we are crossing the suppliers. So we should pick here a crossed study or a crossed and nested because we have this crossed here, this part here where we are changing the suppliers. This specific part of our study is crossed, but the parts are nested. Each part belongs to a specific combination, okay? So we could use this crossed then nested option. I have a message here saying that we cannot have these continuous values here, so we have to change this for nominal because they are sources of variation. So I can come back there and run it again. So now it's done, okay? And we have here our Pareto. Let's sort by column. And we have the first of our Pareto is rubber supplier interacting with glue supplier. This is so important to know when we have an interaction that is strong, that is the first or the second one in our Pareto. So understanding this interaction, we can run different graphs. So I can click here, this red button, relaunch analysis. We go directly to this launch platform. We can take off part, for example, and we have a more easy graph to understand what is happening here. This graph here is about the standard deviation. So each bar here has its own variation. So the standard deviation of each bar is here. So the biggest variation is here because the standard deviation is bigger there. So I don't need this right now. I want to connect the cell means here, and we have a very interesting situation because we can see that we have an interaction. That interaction that is shown here, we can understand this interaction here. Look, this one. Why is the first? This is in the first of the Pareto because we have this situation when we combine the rubber supplier number one with the glue supplier one and two. When we pick the number two, the values are bigger. But when we change the rubber supplier, it's the opposite. The number two here is lower, is smaller than the number one. So we have an interaction. And if I change the position here, we can see something that is very important for our investigation because when I when I choose the glue supplier number two, I have a robust situation because if I need to have a stable process, I should pick the glue supplier number two because I'm not depending on the rubber supplier one or two to have a stable process. If I pick this one, I can choose the cheapest rubber supplier here, and I will have a process around 260 kilos. It's not a good process because we would like to have at least 300, but I'm not depending on the rubber supplier because if I change the glue supplier, I will depend on the rubber supplier to have big or small results. So this is a very interesting graph that could explain the interaction. Okay, so this is what I should or I would do in JMP. There's no sense running a control chart, for example. I will run a control chart to you to understand what is happening here. So I have an unstable process because uh, I'm changing the supplier, so I'm causing this effect, I'm causing this change. So it's not fair, it's not a process over time, it's not a measurement that I'm doing over time to understand the voice of our process. So this is not stable. We have different suppliers. We will cause this, okay? So it's not fair is all is also not fair running a process capability, for example, because we are changing things. Okay, so this is what we can do in JMP. Let's do it now in Minitab. So let's copy this data and let's paste it here. So exactly the same data points. So let's run a variability. Variability chart, response here. The factors, I don't need the lab because lab is not varying. Oops, I have to click here. Rubber supplier, glue supplier, and part. I will not put measure here because measure is the same as part. So what I need is here. We have the same graph, thanks God, right? But cannot I cannot put references line here. So this is something that I told you because I'm limited here. I have a lot of different graphs here as jump, but I'm I'm limited, so I will put this graph there. If I were using the desktop app, I could do this, okay? So let's be very clear. So now let's look for these various components. Stats, ANOVA, and here this is something that I don't like because I have to pick this one. So factors, rubber supplier, glue supplier, and part. And we have these various components here where we have rubber suppliers, 25%, glue supplier 68%, and part 63%. I cannot copy this picture, so I have to use my capture application here. So let's capture this picture. Control C, Control V. And now for me is something that if I were using Minitab, I won't be able to see this interaction. And this is the most important answer that this COV is giving to us. So this could change the perspective. This could change the way of investigation, the approach, the action. So for me, at this moment is something that we could already do here because JMP is earning a new trophy here because the range of features or the customization and interactive here, JMP is so much better. I don't know if you that are watching that is very addicted to Minitab, if you know how to run an analysis that could give me this interaction, please let me this in the comments to me to understand and to not give my students the wrong answer or the wrong training, okay? And if I don't, maybe in a hurry, okay, in a hurry, if I analyzing this data with Minitab and I don't see the interaction, I see that glue supplier is causing the biggest variation here in my process, so I should take a look at the glue supplier. So probably I would run a new variability with glue supplier and that's it. Okay, so I would have this glue supplier and okay, it's a nice graph. It's a very nice graph because I would focus in the glue supplier. It's not a nice graph and a beautiful. I think Jump is generating more beautiful graphs, okay? It's is more fancy, I don't know, is beautiful. Here is like old. I don't know how to explain, but I think the resolution could be better here, okay? I don't know what you think. Please let me in the comments below and let's talk about it. I think there is still room for improvement. So this is something that I would finish the analysis here saying to people that okay, the glue supplier number two, we have less variation. Is the same conclusion here, but we would miss this interaction information. Okay, so that's it. Let's move to DOE. Before starting explaining here, let's do a quick review what a DOE is. Okay, so every single investigator they should run this DOE planning form before running a DOE to guarantee that everything is very well planned. Okay, so this is a DOE planning form. We have our goals, we have our project details, titles, the responsible, the material that will be used. We have here five factors at two levels. We have the glue quantity, 0.23 grams or 0.45 grams. We have the ring fixation method that could be manual or could be assisted. We have the ring fixation time, 5 seconds or 15 seconds. We have the cover surface cleaning, no cleaning or with cleaning, and we have the glue application position, can be at the ring or on cover, okay? We have a part here about the noise strategies. So we have an FRD, our factor relationship diagram, where we have our design here. So we have five factors, 16 different combinations that we call treatments. Is a fractional factorial DOE with a lot of different suppliers combinations here that we will handle at noises as replicates. So we will consider that at a green belt level, we will consider these different combinations of suppliers of glue and rubber suppliers as noises, and we will analyze it as a replicated DOE. If we were talking about a black belt level, we would analyze this completely different, considering that we had a CLV within a DOE, so the analysis is a little bit different. But here at a green belt level, we will consider this as replicates within the treatments, okay? As we have a fractional DOE, 16 treatments, five factors at two levels, we cannot ignore that we have a singularity details. We have some confounding matrix here. And additionally, we have here our 15 degrees of freedom that will be used to analyze the DOE. Okay, so all that said, let's move on to DOE data. We have here our data table with 128 data points. So let's start the analysis using Minitab. Okay, so let's start with this analysis. DOE practical. I have a blank project here. Let's paste the data here. Move. Okay, I pasted in the wrong cell. So, okay, the first thing that we should do here in DOE analysis should be the practical analysis. So we want to understand if we have good data to move on to the graphical analysis. So what is a practical analysis? Is to understand if we generated variation, if we achieved the goal about at least 300 kilos. We have to understand to see if we have special causes or not. So we should, a very good graph to run this analysis is the overlay plot. Is a graph that we sort the data from the smallest to the biggest, and we put in a line, in a connected line, to understand the variation that we had in our experiment. So here in this web app, I'm very limited. I cannot change the cells here. I would like to order the data to sort from the smallest to the biggest. So I will have to come back to my DOE data plan. I will sort this data. I will have to create a column called order. You will understand why, but I have to do this in my Excel file. So I will copy this data. I will paste it here again. Okay, now I have these two columns sorted and a new column called order just to run the graph that I want. So a scatter plot graph, simple one. My y variable is extraction force and the x variable is the order. I will click here in options and I will connect line and I will have this very simple scatter plot graph where I can see that I have a good data to move on to the graphical analysis because we achieved the at least 300 kilos. We have a very good variation. We have parts that were assembled and we have almost 400 kilos. We have some combinations of factors that we didn't achieve 100 kilos. So we have a very good variation. We don't have special calls. So we are good to go and to move on to the graphical analysis. And now look what happened here. I was struggled here. I was suffering trying to analyze this, and now I figure out how I have to run this analysis because if we just copied and pasted here our data table from an Excel file, I'm not able to come here in stats, DOE, screening, or factorial and analyze factorial designs. Not able. So what I had to do here is something very, very boring. I had to create, okay, let's start a new DOE. So let's DOE factorial, create factorial design. So two-level factorial, five different factors. Okay, I have different designs. I want this one, resolution 5, 16 runs. I need how many replicates? Let's be sure. Okay, 8 replicates by combination. So for corner points, 8 replicates. Okay. So now we have now we should have 128 runs. Let's see. Okay, okay, it's here. But now we have to match these columns here with this data. Okay, so the order of the combinations here, they are different. Okay, so this is very, very critical. So let's organize this data from assembly. Look that we have the treatment, the combination number one being replicated like 8 times. So we have exactly 8 the 8 same combinations here, another 8 here, another 8. So they are the treatments. Okay. So we have to copy this information here. Let's copy from here the A, B, C, D, E. Control C. Let's paste it here. Let's organize this sorting from E, D, C, B, and E. Now we have the combinations being exactly the same. So now I can copy this column and paste it here. And now I can copy this information, go there and paste here. So now we have our extraction force being exactly the same as we had in our Excel file. Okay, now let's see if it works. DOE factorial. Okay, analyze factorial design. So just because of that, Just because of that, I hope that in the desktop app it will be easier. Look, another point here, ease of use, the user experience. If you don't know how to plan a DOE, organize your data table, you will be completely wrong. Okay, so let's come back here. I'm really pissed off about this because this is so basic. Terms, okay, our 15 degrees of freedom, they are here. Options, no transformation, covariates, graphs, Pareto, okay. Results, okay, nothing to change here. Okay. Coded coefficients. I need a Pareto. Where's the Pareto? Model analysis of variance, regression equation, alias. Here it is, our Pareto. So copy graph. Let's come back to the DOE analysis, and we have now our Pareto. So the first one here is the degree of freedom A, the factor B. We have an interaction, a strong interaction here, and the factor C, and all the rest, they are not statistically significant because they are under this red line here. So we have four main factors or degrees of freedom that are changing our results. So we have this interaction AB. This graphical analysis, we should analyze the interaction. So let's do it. Stat, DOE, factorial, factorial plots. So the interaction that we want to analyze is the AB. So let's take off the rest of the factors and just AB. Okay, and we have the interaction plot here. So let's copy this graph and paste it here. So what's happening here? If we put the factor A in the plus level, okay, the +1 level here, what is the factor A? Let's check. The A is the glue quantity. So if we put more glue, 0.45 grams, we could pick either the B minus or B plus, and we would have bigger the best values because we are talking about achieving 300 kilos. So if we choose A plus and B minus, we would have this value around 300. And if we pick A plus and B plus, this red square here, we would have more than 300 kilos. So this is something very important to understand. Every time that we have an interaction being one of the first or the second or third in our Pareto, we should analyze it, understand it, and take some actions about it. Okay, so this is our interaction plot being done by Minitab web application. So let's move on. Let's move on to our quantitative analysis, our reduced model. So once I know that only these degrees of freedom are really affecting my response variable, I can run a reduced model. So instead of having a very big equation like this one here, this equation is so much big there, and there's a lot of things that doesn't matter. They don't affect the response variable. So I should run another DOE analysis. I could do this. These terms, only these ones, A, B, C, and the interaction AB. So I just took off all the rest of them that they are not having any effect. So I have now a reduced model. And what are we interested here? So let's just take some pictures here. Our model summary, this is something very important to us because we will have a model, a reduced model. Oops, it's here. A reduced model that with only 4 degrees of freedom, we are having like 96% of representation of our data representation. So this equation here, this equation here that we have also to take a picture here. This is so much boring. So let's copy it here. We have this regression equation. It's representing like 98% of our data points. And okay, the Pareto is here. And another thing that is important, it's here. So we have a model being represented by only 4 degrees of freedom, and those 4 degrees of freedom they are generating like 800 more variation than the errors, the 123 degrees of freedom that were given to the errors because we just reduced our model. So this quantitative analysis is very, very important. The last but not least graph that we need here is our prediction profiler. So let's do it. And now the last part of the analysis with this reduced model, we can go there in DOE, factorial, and use this response optimizer. So what we want to do with the response? We have to maximize, we have to have numbers, values, responses, scenarios that bigger than 300 kilos. So we just put to maximize, and we have here this graph where we consider only A, B, and C. So this is very, very nice. We can change here the values and we can maximize all the situations. So if we put A in the level plus, B at the level plus, and C at the level plus, we will have extraction force about 351 kilos. So this is amazing. We just got a very, very good result that we can put here. So final conclusions here, it would be like let's pick the glue quantity. Let's put the amount of glue in 0.45. Let's use the assisted ring fixation method, and the C is +1 as well, and C is let's use 15 seconds for the ring fixation time. So this would be a very, very robust solution, a very maximized solution. So let's change things. Let's see if we can have a faster process. Let's see what happened here. Look, if we do this, this is a very good scenario. Here we can work with different scenarios. This is very, very interesting because if we reduce the fixation time from 15 to 5 seconds from here to here, but guaranteeing that the method is the assisted one, the amount of glue is the 0.45, we can have a faster process and we will still have like 302 kilos of force, of extraction force. So this could be done. This is another scenario that is not so robust because of course we will have some variation between these results in the practice, okay? So but at the same time we have a process that is maybe cheaper, okay? We can produce at least twice more, reducing this time from 15 to 5, okay? So, final conclusions, we could spend a lot of time here running different scenarios. So, that's it. Let's move on and run all this exactly the same analysis in Jump. I will delete these rows here and make it more clear. Okay, so let's go there to Jump. Okay, so now let's analyze the DOE data in the JMP software. So let's copy our data table and paste it with the column name. So the first analysis is the practical analysis, where I just have to click here and sort ascending this column, graph, legacy, overlay plot, the Y in the Y field here, clicked OK, add a line, and that graph that I had using Minitab on web that I had to organize all the data table here, ordering or sorting the data, everything here in Jump, I just made it in a few seconds. So I will add a reference line here because I can, lower specification limit, that blue dashed line, and here we can see that we have a very good result. We can change here the the size of the graph. I just copied the OA analysis and let's paste it here. So the same graph, same conclusions. Now I need this graph and this graph. So how can I do this? Using Jump, analyze, fit model, the Y here, and what are the effects? What are the degrees of freedom? So if you remember, we had a plan. So the terms that we need, they are here. So every single main factor and every single two-way interactions factor. So let's select all of them. We have 2 degrees here, factorial 2 degrees. So we have all the 15 factors here. We have a lot of information, and what I need is the sorted estimates parameter. So I will copy this guy here and I will paste it in here. So we can compare this graph to this graph, and we can see that Jump is offering something more, let's say, beautiful or cleaning or clean. So, okay, the colors are different. We have everything to the right. Here I have all the effects that are negatives, or in another way, in other words, if when you change from minus to plus, this degree of freedom will decrease your response variable. So this bar is to the left. Okay, so this is something interesting. Here we don't have numbers, we don't have the effects. Here we have everything, even the p-values. Okay, so the interaction plots, we can have all the interaction plots here, all of them here, but I would like to have only with the AB. So to run the AB, interaction, I need A, I need B, and I need AB. So now I can ask for jump, give me the interaction plot. So I have this interaction plot here, and now it's a fair comparison. Okay, we have this against this and this one against this one. Same data, same conclusions. Let's move to the quantitative analysis and get these numbers. So let's close this one. We can reduce our model just by clicking here. We have effect summary when I can remove everything that I don't need. So I just removed with a single click, and now I can see my summary fit and my ANOVA and my prediction expression. So everything that I need is here. They are exactly the same values. I just paste it here and all the numbers are the same. 96% of R square, 869 for F radio, and our prediction expression. So now let's play with the prediction profiler. I really like the prediction profiler in Jump because, in my opinion, is one of the most powerful tools that Jump offers to us because we have a lot of options here. We can play is smooth, is easy to understand. We can maximize. We can match a target. Minitab is always doing this, but I think Jump is more beautiful, is easier to run the analysis. I don't know why, but when you use both softwares, it's very easy to understand how much better is Jump when performing this type of analysis, okay? And the other, I will do exactly the same here, just copying and pasting the same scenarios that we've done here using Minitab. Look the difference. For me, this is completely different. Let's focus on this image. Look, this is like, I don't know, 1980s when we started having the Six Sigma methodology in the world, like old graph, old school, is not fancy. The resolution is not good. It's like those programs that we used when we were young, you know. And here you have something more beautiful. Is in a report, it would be so much greater than this. So people have to evolve in this field, okay? So let's come back to the prediction profiler in Jump because I would like to show you a little bit more things here. For example, data points. You can add the data points. You can add overlaid interactions. For example, I'm working with this scenario, and for example, I would like to have this line here instead of this one. So B 0.8. If you change this for 0.8, you will have this line here. So you can move things very in a very good way. You can see what more the prediction intervals is not the confidence intervals. You have the prediction intervals as well. This shadow, this gray shadow with these green bounds here. So there are a lot of statistics involved in this prediction profiler. You can simulate things. For example, let's imagine that you choose to get this A plus, B plus, and C minus. Okay, This is more glue, this is assisted method, and here you had 15 seconds or 5 seconds. So let's put in 5 seconds to have a faster process. But these 5 seconds can vary how much. So you can add here this variation in time. This is a method, so it's fixed. And here you can also have a variation in the amount of glue. So let's put a variation around this level, and let's simulate 10,000 assemblies. So let's simulate this and we will have this variation. You can even simulate it to a table and you have there 10,000 uh, uh, situations or assembles that were done using this simulation that you just put here. Okay, so this is very nice, but now let's finish and let's move to the validation data. I will try to be quick here, but what do we have here in our validation data is I will run a variability chart, okay, just to understand what happened, how it was done. Oops, sorry, I don't need the measure. I don't need the measure. I will recall this and take off the measure. Okay, now it's good. Connect lines. Let's put our lowest specification limit. What happened here? Everything that was done was good. But what was done? Knowing that if we put this combination of factors here, for example, we would have a very strong and good result, achieving our lower specification limit about 300 kilos. We just went there, the investigator went there and ran a validation data with 20 parts, changing or mixing the glue and rubber suppliers, trying to be robust against this situation. Because imagine that we have to have this dual sourcing, for example. We have sometimes to change the glue supplier or the rubber supplier, but if we guarantee that we will use at least 0.40 grams of glue and using the assisted fixation method and doing this with 10 or 12 or 15 seconds, we will be robust against this supplier variation. So this is a very good scenario to be validated. And what more can we do here using JMP? We can run a process capability analysis. So I will put here in this distribution, the Y column is our response variable. We will consider everything as a normal curve here. Process capability, the lower specification limit is here. And now we have this analysis. So let's put it here. And we have here the overall sigma, and we have the within sigma, and we have the within sigma being used to calculate the CPK, and the overall sigma being used to calculate the PPK. Both values are excellent, and our expected non-conformance is practically zero. So let's run this same analysis using Minitab and see what happens. So let's copy this data and paste there on our Minitab web application. I won't run a variability chart because we have already done this and it's almost the same. So I will go directly to quality tools, capability analysis, normal, and I have this column subgroup size. Oh my goodness. Why should I do that? Use a constant or an ID column. So considering that we had 5 parts for each combination, so I will use 5 parts. The lower spec is here. Let's click on OK and let's copy this picture and paste there. So let's compare. Look again, 1980s, 1990s, and 2020, 2020s and 1980s. So this is very old-fashioned, let's say. Sorry about that, Minitab, but you should evolve this. Okay, so PPK 1.94 and CPK 190, and here 2.20 or 2.203. Why is that? Where are the standard deviation? Overall is the same, within is different. Why is different? Because of the subgroup. Let's try another one. Stat, quality, capability analysis, normal. Let's use 2 because within sigma we are using the moving range mean divided by D2 considering subgroup size about 2. Let's see. Uh-oh, is different. Okay, I will let this challenge to you. If you that are watching this video that is addicted to Minitab, explain to me why this within sigma is different um, from the within sigma calculated by JMP. Okay, the results are different, but they are great. I think the risk here is very, very low to have a wrong conclusion. But I don't like this situation where we should have the same numbers. Okay, so that's it. Let's move to the final conclusions of this video. So before doing the final considerations here, let's summarize what happened here. So we have 4 trophies for jump and 0 for Minitab because, first of all, for all the users that are running the analysis using Mac, uh, they will have problems using Minitab. So availability, 1 trophy for jump. Usability, ease of use, user experience, understanding of analysis, another trophy. Functionality, range of features, customization, and interactivity, so another trophy for jump. And the performance is speed and the statistics involved in analysis, another trophy. So the end of story, 4 to 0 for jump. So now let's move on to the final considerations. So, dear viewers, we have reached the end of this green belt comparison. And in my humble opinion, it's very, very difficult for Minitab to win this battle. Even if we were using the dedicated Mac OS application, because Jump is far more advanced in terms of usability, clarity of information, statistical capabilities, and the overall user experience. Okay, I hope you enjoyed this video. If you have any comments, please write them below. Don't forget to like the video and share with colleagues who might find it useful. Okay. Thank you so much for making it this far. I know it's difficult. It's a lot of information, but if you like Six Sigma as much as I like. I think you made this far. Feel free to reach out if you are interested in any Six Sigma training. It would be a great pleasure to help you and your company grow and evolve toward operational excellence. Bye bye. Thanks for watching.